Test.
So it's on now, right? Or?
Yeah.
Okay.
Maybe I can say a few
Yes.
All right. Good morning, everyone. I'm gonna give the first few minutes to the Inclusive AI Mentorship Program, and I'm gonna tell you what this is all about.
Yeah, thanks. So great to quickly be here. So I'm Maartje, and this is Melika. Some of you may have heard about us already. So we are here to quickly present the Inclusive AI program, which is a mentorship program for underrepresented groups in the Master AI. So what do we do? All kinds of things. So basically the first thing is a mentorship program, so where you would be matched with a senior or like PhD student, typically, sometimes like assistant professor level postdoc, for some mentorship. So what we do is things like that. So ask for advice like CV or motivation letter. But we also have some events like drinks, and like went to a conference a couple of months ago. So all kinds of things to kind of help you get a bit familiar with the academic world, basically. So what does that mean, underrepresented groups? Well, we really don't really define that, but things you can think about is, I don't know, maybe you're the first person from your family to go to university, or maybe you're from the LGBTQ plus community, maybe you're a person of color, maybe you are a woman, maybe, well, whatever, you name it. It's not strict. If you feel like this could be something for you, please sign up via the link or the QR code. Yeah, if there's any questions, also happy to answer. Too early for questions? Yeah, so we also have an email address where you can also ask questions. We will be able to answer them there. Yeah, if there is nothing, hope to see your applications come in soon. I mean, application sounds maybe a bit much. Like it's really just quickly sign up so that we know your name. All right. Thanks so much.
All right, let's start. Yeah, generally, like, I definitely recommend doing stuff besides studying. Like, I did a bunch of student organizations while studying. I know it's quite busy and all, but I don't think anyone usually regrets working in these organizations or doing anything besides studying. All right, so let's start. So first, just a brief overview of what we did last time. We talked about, okay, we know how to optimize it. That was 1 week ago. We can use the gradients. We can compute the gradients with backpropagation, but neural networks are pretty tricky to optimize still, so the gradient can get stuck in all kinds of ways. One example was the ill conditioning. We also played a bit around with this tool and some other optimization things to actually see the loss landscape, and then talked a bit about optimizations. So today's lecture, I thought we'll go through backpropagation one more time in real detail. No, we're not. So, I mean, the people that have the slides already knew this was coming, but today we're actually going to talk about normalization, regularization, and hyperparameters. So regularization. I spoke a bit about this, the difference between these two things the last time already, but I thought I'd start the lecture with the following exercise, that you turn to your neighbor, or to your neighbors if you're in a three group, and discuss why the left one might be better, but also find a couple of reasons why the right one might be better. And I'll give you 2 minutes or so, and then we'll be back. And by that time, everyone is probably woken up as well. So, all right. Hey. Yeah, it's exercise at the moment, so.
We want to test night the lecture. What I found interesting is so I come from math, and I saw obviously differential geometry and algebraic topology, and then there's a lot of times like an ant going through some weird structure, and I was like, why are physicists so obsessed about that? And now like there's actually like it's an optimization problem.
Oh yes, yes.
Yeah.
Yes. Yeah. We can talk more about it in the break. So at the moment, I'm asking students to find reasons why this one might be better sometimes, and why that one might be better.
Oh, so I did miss the beginning.
Yeah, yes, you did miss the beginning. So just 1 more minute, so maybe you can turn to your back neighbors and get some summary of what they've come up. All right, let's continue. Thanks for discussing. I hope you did find reasons for both, because yeah, sometimes one might be better, sometimes the other might be better. Pretty sure you figured that one out. Yeah, and I'll leave this to discuss further in the breaks, and you can discuss with your students why exactly that might be the case. Just one point here, that just sort of digression with the natural world, with physics. Obviously, neural network being an engineering science, deep learning is far away from all of that stuff. But even in nature, you see that sometimes a very simple relationship isn't the truth, right? So you had the gravitation equation from Newton, which was nice and simple, but actually Einstein made it much more general, so to say, and added a bunch of correction terms which describes the fundamental nature much better, perhaps still not perfectly. So maybe there's even more correction terms coming, which ends up with a quite difficult problem. All right, so today we're going to start talking about the bias-variance trade-off that exists when learning neural networks. So remember, at the end of the optimization procedure, or during the optimization procedure, we get one set of weights. And these weights are typically point estimators for the correct weights that we want. And point estimators can be defined as the single best prediction of some quantity of interest. In this case, we have a whole list of parameters, but still we just have one parameter for one estimate for each parameter. And so we can write this as the following. So theta is now our set of parameters, and g is the estimation procedure. In this case, it was, for example, using SGD along with the data samples. And the good estimator that we are sort of trying to find is, of course, the one that gives us output, which is close to the underlying theta, which is close to producing how the data was generated. All right. Now, the heading says bias-variance trade-off. what is the bias? The bias is typically the error that comes from wrong assumptions in the learning algorithm. And by learning algorithm, we mean this quite broadly. So it could be that the model is ill-specified. It doesn't fit the real data. And if it doesn't fit, it cannot really match the data it's seeing. So typically, if you have a high bias, your model would be underfitting the target outputs. The variance is a different kind of error, which comes from sensitivity to small fluctuations in the training data. And high variance can result from basically the algorithm being too powerful in turn and modeling the noise that comes naturally from observation. And you can think of various kinds of noise. So this could be simply noise in how you captured the data. This could be noise in the natural physics phenomenon. So if you have a physical camera, you have naturally noise at every pixel level, depending how good the camera is. Just take a picture at night and you'll see the kind of noise that you can get. And typically, linear models often have a very high bias, but a low variance. And nonlinear machine learning algorithms, such as deep learning, have a low bias, but a high variance. And I'm sure you've seen this curve already. And here you have on the x-axis the optimal capacity. So you have a capacity of the model that you're trying to learn the parameters from. And on the y-axis, you have these errors. A linear model, as I said, is typically all the way to the left side. So it has a low variance, but a high bias. And then once you increase the capacity of such models, for example, by adding layers in the case of a neural network or by doing some other more sophisticated things, you'll typically achieve a point where your generalization error is low. That means the error on your test set is low. And then something happens where the generalization error increases. Why does it increase? Because at that point, the model or the capacity is already that high that it can start modeling the noise that's in the training data already. And once it starts doing that, we're basically at the first slide, or the interactive slide, where you start fitting all these noises which don't really belong to the fundamental true distribution. But your model is capable of fitting it, so it will try to really fit these, and that reduces the loss, and you end up with worse performance on a held-out generalization test data set. More visually and in 2D, I find this quite useful to remember what these different things mean. So low variance, low bias, you hit the spot. High variance, low bias means, yeah, your average is sort of close to where you want it to be, but it spreads around quite a bit. And then the other places you obviously don't want to be. With a high bias means you're not even if you're very precise, even if your variance is very low, you end up at a spot where you don't want to be. However, as last time I've already foreshadowed that even large neural networks work. So basically this lecture will be about how we can make them work. And for this, let's talk about overfitting. It's one of the most important aspects when we train neural networks is to avoid this phenomenon of overfitting. So generally, visually, you can see it at the bottom. So the blue curve here is the output of the model. And in this case, it's a simple 1D prediction regression problem. If the model has a perfect fit, obviously it can predict a line through the points and be very close to the ground truth distribution. Once we start overfitting, you can see that it's going through much more points, but the function has these weird shapes between the points, which is of course not great because, as I said, once you sample points that are in between these points, for example, pick any point in the first third of the picture where you don't have much observations, you can see that the overfitted model will give you pretty terrible predictions. Yeah, that's because of the noise typically. So why do neural networks pick up this sort of noise? There's a couple of reasons. So as I said, one is the complexity of networks is too high, at least for this particular problem that you're looking at. The data is in turn too easy or too little amount of data that it can pick up these sort of things. If you don't have enough data, it will pick up these sort of things. It can also be that yeah, if you have then new samples, they will have a, yeah, that's just the result, basically. This is not a reason. This is the result, what you get if you have high overfitting going on. One sample that actually puts this a bit back into the real world is this actual picture. So there's a data set where you're trying to detect different animal types. And I think in this data set, it was basically that every image of a horse, or lots of images of horses, had this watermark at the top, at the bottom left. And then on the right-hand side, you see what they did is sort of visualize where the model was looking at. And of course, it wasn't really looking at the horse, because it would be much easier to just look at the bottom left corner to see whether there was a watermark or not. And this is also nice, because once you have a test data set, which by chance has a much lower amount of watermarks per horse image, or doesn't even have these watermarks, it will fail completely. So yeah, neural networks, they typically have, as I said, millions of parameters, if not a lot more. And the data set is typically smaller than the number of parameters. So this is the fundamental difference to stuff like linear regression, logistic regression, or even random forests and other machine learning methods, which makes the overfitting the grave danger. And to give you a great loss, great cost function for the training data set, but terrible performance for the test set. All right, and what we're going to do, and this is the first part, is do regularization. Another example of, before we go there, another example of overfitting for neural networks is the following paper where, I mean, you can read the left-hand side, but the main message is these neural networks easily fit random labels. And this is for an image data set in this case. What they did is they had a data set with ground truth labels, in this case 10 of them, cipher 10, and they simply shuffled the labels for each image. So now each image would have a random label, completely random. And now the thing I want you to focus is the blue curve, which is the training curve. Here you can see the steps that gradient descent has taken. The blue curve is if you have the true labels, and the green curve is if you have shuffled labels. And you can see that on the training data set, it takes a bit longer, but eventually you get pretty much zero loss, even if you have shuffled labels. So deep neural networks can basically fit anything you give it to them, even if the labels are not coherent at all. Obviously, if you then test it on a real test set with the ground truth labels, you'll get performance of 10%, which is 1 over 10, because there's 10 categories, so it's just chance level. Right, and before we go to regularization, even this plot isn't the full story. So there's been a big update to this curve, which is called the double descent curve. And so it's a lot of pictures, so let's start first from the top left. So A is the case of an MNIST data set, so it's a really easy data set. And you can see that the training loss goes down really quickly to 0, so you've perfectly fit the training data set. And for the test data set, you can see that actually you don't see any bias variance trade-off curve whatsoever. It simply keeps going down. This shows that the data set is simply extremely easy in this case. However, for the B and CD, as we'll see, but let's focus on the B first, you first see this usual bias variance trade-off curve, right? You see that the generalization error on the test set starts going up again, but then this is why it's called double descent, you can start that it starts going down, and it ends up even at the lower place where it was at the best, at the optimal capacity sort of place. While the training loss is basically 0 all the way. No matter what kind of hidden size you have that's bigger than that. And you can see the same for C and D. There it's a bit more pronounced if you actually have noise in the data set. Because then it's really overfitting to it in a bad manner. And the dashed line in particular is where the network capacity pretty much exactly matches the data set size. So the dashed line is actually number of samples times the size of the samples equals the number of parameters. And you can see exactly when that happens, that's when you have the worst test error. So exactly when that happens, the network is picking up exactly everything that's in there, but once it has more capacity, it stops doing that. And so that's a really weird thing. And the question is, why is it doing that? And this has been only found out in 2019. The reasons are hypothesized to be smoothness and regularization. And what do we mean by smoothness and regularization? So all of these three plots have a loss of 0. As you can see on the training data set, the curve goes through all of them. However, you can make a reasonable guess which one of these works best, right? So the smoother one works better. And if we just take this as a starting point for our hypothesis, you can make a simple experiment where you take an MLP network and try to regress this function. And you can change the number of hidden units. And actually what you see is that for all of these, pretty much you have the loss is 0. As you can see, if you have 6 hidden units, you can fit, it's a function with at least 6 parameters, right? So you can fit all of these data points you're seeing. But once you start increasing the hidden units, the function that you're getting is actually much smoother. So as long as the function you're trying to fit is quite smooth, simply using more parameter actually makes it better. Yes?
I'm confused. So the first graph, the original one, was mathematically given. So these were empirically?
The first plot, the typical, I mean, you can still see this bias variance curve here, right? This is simply what you have here. And then this first quarter, third, of the picture is a normal bias variance curve.
Yeah.
This part, yeah, I mean, all of this is now empirical. These are experiments. Typically, what people have thought is that, okay, you would just continue fitting noise, and that's where it stays, right? At some point, you have fit all the noise, and that's just going to stay terrible. But actually, what you're seeing, at least for a couple of neural networks, and this is not everywhere the case, and I'll come to that why this isn't relevant everywhere. But once you've done that, the smoothness basically kicks in. And this is hypothesized, at least, to be the reason why the performance starts increasing again. Before I talk about why this might not be relevant for all the cases, is, well, just as a theory point, this is really important because what we're seeing is that larger and larger models, especially for language modeling and NLP, but also for vision, actually require much less compute to get the same performance. So for example, at the same number of inputs here's tokens processed, for example, at 2 to the power of 9 or whatever, you can see that the models in blue, which have much less parameters, end up performing much worse than the larger models. So it's still an open question whether this double descent applies to these models, but there's definitely a connection, and that is an interesting point at the moment about scale. Just a few notes, double descent in practice. It's tricky because, as I said, you need the capacity of the model to be as big as the training data set. So this really, for most data sets, we're not there. So you need this very toyish data sets or small data sets and huge models to get there. So we still need this lecture. So you cannot just make the model bigger. All right, so let's start with regularization. Generally, this is a very broad term that refers to techniques that can help the neural network learn. And pretty much everything you do that helps the neural network learn in some manner, we call regularization quite often. So the typical ones that we're going to go through are L2, L1, regularizations, early stopping, dropout, but there's a lot more. And if you write a paper and you're trying to learn a problem and you come up with a way that helps it learn better, you typically call it regularization as well. All right, let's start with L2 regularization. This is the most common of all. So typically it's called weight decay, as you'll see in a bit why it's called this way, or ridge regression. If you remember from last time or 2 times ago as well, we had this regularization term omega, which was simply dependent on the weights itself. So it wasn't dependent on the input, it wasn't dependent on the output or the prediction, it was simply omega of W. And in this case, omega of W is the sum over the absolute values, the squared values of the weights. So as I'm showing here. We're taking the 1/2 here because if you then differentiate, this 1/2 will cancel with the power of 2, which is nice, but obviously you don't need to do that. It encourages the weights towards 0, as we'll see in a bit, and you can actually derive this regularization using some theory that you assume that the weights of the neural network follow a Gaussian prior centered around 0. So in certain circumstances, they can deviate from 0, but the average should be 0, and this is what you end up with. The loss function, as I said, then basically looks as follows. You're trying to get the weights using the optimization procedure. By doing this, by adding simply this additional omega term to your loss function. In this case, we're scaling it with a parameter lambda, which can simply control how much this matters. If you want your weight decay, your L2 regularization, to only matter just a tiny bit, then you pick a small lambda. This one is a trickier parameter to choose, as you can try out in the playground demo we had the last time. If you pick it too big, then your neural network will just try to make all the weights 0 and it won't learn anything. If it's too small, it won't have any effect at all sometimes. So, and now you can see why it's called weight decay. So if you simply take the derivative of the above loss function, you can see that you end up with a term that includes W. And so and this term has a factor of lambda before it, and you're updating the weights by having the current set of weights minus the gradient and so on. And so now the gradient of the loss function includes this weights W, so you can simply put this into one factor, as we've done here, and you can see that now the more steps you go, the further you can see the weights decaying, basically. And yeah, you can see that this has an exponential decay formula, because 1 minus lambda is usually picked to be low, usually about 0.1, 0.01, or even lower. This is a hyperparameter which you need to tune. We'll be talking about hyperparameters and how to tune them later on. All right. L1 regularization, as you might be able to imagine, is simply the following. Instead of taking the square of the weights, we're simply taking the absolute values. Now, as you'll see in the loss function, this means we're not adding anything in the gradient descent update that's dependent on the size of the weights itself, because if you take the derivative of that, you simply get a minus 1/2 or plus 1/2, so a constant factor with an alternating sign. And again, you can derive this now not with a Gaussian prior distribution on the weights, but instead with an isotropic Laplacian, which looks slightly different. So let's do the same thing here. So now we have the lambda half times the sum of the absolute values. We now take the derivative of that, and we end up with this. What you see here is that it's basically dependent on the sign itself. And there should be a W here. So it's only dependent on the sign. So this W should cancel out. L1, in turn, encourages, of course, lower weights, because you have an additional cost that's dependent on the amount of weight. But more importantly, it encourages sparse weights. What do we mean by sparse weights? Sparse weights are the following. So this picture can be a bit confusing, but if you go through it step by step, it's quite easy. So you have, on both pictures at the bottom right, you have a model with two parameters, W1 and W2. In red, we've depicted the loss function. W with a hat, with a nice party hat, that gives us the lowest loss function possible. Everything around that, the further away you go, the higher the loss. And now you can see at one of these similar loss curves, similar equi-loss ellipses basically, at one of these, it's touching this diamond-shaped L1 regularization. And at this point, you can see if you go any further with your loss function, you will have a worse loss. And at the same time, within the surface of this diamond-shaped thing, you have the same amount of L1 regularization. So where these two meet is where your loss function is optimal. The same goes for L2, except in L2, it doesn't really matter where you end up now. As long as you have this, as long as, you're within this surface, it doesn't really matter where you end up. An easier way, or like the same but slightly different way, is to think as following. Think of the equal cost line of here depicted at H0. And no matter how it's looking, it could be like slightly bent or slightly different slope. But in almost all cases, except when the slope is exactly minus x2 and x1, except in that case, you can see why L1 encourages sparse solutions, and L2 simply requires lower solutions, lower weights. And in this case, here, x1 and x2 are the weights. In practice, it looks like the following. So for L2, here you're fitting a model, and this is just an example I've taken from scikit-learn, which is a machine learning package in Python. Here the lambda is the equivalent of our alpha parameter. So if alpha is very low, we're not doing any regularization at all, and we're simply fitting a linear model to some target. And you can see the parameters are, all over the place. Some are minus 100, some are plus 220, etc. And then you're gradually increasing the value of alpha as you go from the right to the left. And what you're seeing is that now you're putting more pressure on the weights to be low, all the way to, once you have it to 10 to the minus 3, they're basically close to 0. So at that point, you've decayed the weights so much that they require to be as low as possible. So basically, at that point, you can be sure that your loss function, you have to analyze it, of course, but at that point, you can be fairly sure that the major part of your loss function is only stemming from this regularization term and not anymore from your function fitting term, which is also not what you want. So you need to find the right balance here. And the right balance, as we'll go later, you can find by having a validation set. Oh, yes, sorry. Yeah, so if you have the L1 shape, the easiest thing is, so what is the L1 cost? The L1 cost is simply, in this case, we had the sum of Wi, right? And in this case, it's simply W1 plus W2 and the absolute values. And now, if you set this, for example, to be a constant 2, and then you can simply write this out as, this means W2 is simply 2 minus W1 for one of the quadrants, and 2 minus W1 gives you this part of the curve. And then you can solve it for all the other parts of the quadrant, so you need to flip the signs. But then at all of these places, no matter where you move along this curve, you get the same L1 cost. And this is the same for the L2. The L2 in this case is simply x1 squared plus x2 squared, which is, as it so happens, the definition of a circle. And so that's why you get a circle here. Oh, yeah. And this is how L1 looks. So for now, focus just on the filled lines. So positive lasso is basically doing the same, but only for positive weights. And yeah, you can see that a bunch of these weights eventually drop down to exactly 0. All right, let's go to the third technique of regularization called early stopping. So a simple way to regularize a bunch of parameters is simply by stopping your training early. We do this by simply looking at the validation error, because at some point the validation error might be going up again, and then you simply say, okay, this is it, we're going to stop here. The question is, why does it work? So the reason is that you see these Bayes variance curves not only for the number of and the number of layers, but you see it for all kinds of parameters, all kinds of hyperparameters. For example, weight decay, or the number of training epochs. That's basically another hyperparameter. So early stopping does the following. We simply set a time point where we have the lowest validation set error, which is a held out data set that we're simply going to use for this purpose. It's different from the eventual testing data set. And at this stage, the models have a low variance. They are clearly performing well on the validation set. And so we can describe them as generalizing quite well. And so further training on the training data set, we assume will lead to overfitting. And this is all that there is to early stopping, really. It's commonly used, it's simple. You just need to make sure you have a separate validation set. And of course, you need to be able to save your parameters at that point. You don't know where this point is going to happen exactly. So typically, you keep track of your current validation set performance. And whenever your validation set performance is better than your previous ones, you just save the model. And this can be used with all kinds of other regularization strategies as well. Yep.
But then you're using the validation set for the training. So it's not really a validation set.
So this might be a thing of vocabulary, but how I refer to, or how it's commonly referred to, is you have your training data set, and then you have your testing data set. And this is sort of the real world test, basically. And what you typically then do is you take a bit of your training data set and you call this validation data set. And you simply train on this. So then testing the performance on this one counts or measures a bit of generalization ability. Yeah. And there's, you might have had this in machine learning, there's k-fold cross-validation where you then shift these things around. Then you could have instead this be your validation set and all of this be the training data set and so on. So there's a bunch of things. But of course, neural network training is quite expensive. So you typically just fix this once and do this sort of stuff. Right. So as I said, most hyperparameters actually have such U-shaped curves. So if you have, as I said, if your model will benefit from regularization, you can now think of, instead of having optimal capacity here, you can think of regularization parameter, right? If you don't regularize, your model will overfit. In this case, it would be the reverse. If you don't regularize at all, your model might be really bad. If you regularize too much, your model might also be bad, right? So a lot of parameters have such U-shaped curves. And early stopping works to find these in a quite natural way. These equations, you can test them out yourself, but they show that for a linear model, the regularization constant is proportional to the inverse of the number of training steps. So the number of training steps has a relationship implicitly with how much you've regularized your model. Depicted for neural networks and somewhat in a more visual manner, it looks as follows. So imagine you starting out from some early point of weights that's near the origin, and you keep going up. And as I said, the dashed lines here indicate the same curves for the same amount of regularization. And if you keep going that way, you can stop at an earlier point, which might generalize better. And weight decay, basically you're testing out different weight decay parameters at that point. So as you can see here, so in this case, the weight decay parameter here is alpha, not lambda, and the number of training steps is tau. So tau has this relationship with alpha. So by changing tau, you can change different kinds of alphas very efficiently in a way. Of course, you'll have to try this out yourself. And the nice thing is you get this for free by simply training. So you just keep training for a couple of epochs. And once the validation set performance is lower, you've done your early stopping. And you can say, OK, with early stopping, instead of training 100 epochs, we ended up at 90. Yeah.
The validation loss curve is not strictly decreasing or increasing. So it fluctuates along the way. But then how much of a difference do you accept?
Yes, that's a bit messy. So you're right, like validation, it depends a bit on the data set. And that's what, like for example, for small data sets, you typically see your training loss if you're measuring, for example, it with every batch, it looks like this, right? And your validation sort might be doing something like this. So it's not super easy to trust these curves, right, if they're doing so much of that. With a larger validation set, this typically starts to also to be more smooth. So that's typically what makes this problem a lot more easy. There's a bunch of ways to solve for this zigzagness. You can, for example, average 2 checkpoint weights. You can just say, as long as the performance hasn't increased by a significant amount, 10% of the previous average 5 epochs. Like there's a bunch of heuristics you can use, but in most cases it's not such a big problem because you have a bit more trustworthy validation sets that are larger. If your data set is really tiny, then you train this thing 10 times, and yeah, sometimes you might end up picking a point that's kind of like here, and on a different loss curve you might end up picking something here, and yeah, and then it's still fine. Like you're still averaging this out. And then you can report the standard deviation of the performance. All right. Yes?
But in this case, we need the weights to be centered around 0 as initialization, or does it also work if we center them around any other point? Because now,
yeah. So in this case, they're centered. They start off with low values, and actually, in neural networks, they almost always are centered around 0 anyways. So that actually is the same. But if you, that is a good exercise. If you start your neural networks with randomly extremely high values, I mean, apart from the fact that you will have a lot of difficulty training them, whether early stopping still has the same effect, that might be a good exam question, or a good question actually. Yeah. Anyways, moving on, dropout. This is a very common regularization technique. So let's first think about the problem that it addresses. It addresses a problem known as the co-adaptation phenomenon, where because neural networks are so large, they have so many hidden neurons, they can exhibit highly correlated behavior. So a couple of neurons might be doing the exact same operations that another neuron is doing, or 2 neurons approximate the same thing that another neuron is doing, etc. You have, because there's so much capacity, they can easily learn the same things, even if they're initialized to completely random values. And because if that happens, for example, 5 neurons do roughly the same thing as another neuron, you will have some neurons which are much more important or much more predictive than others, right? So if one neuron is just doing the work of the same thing that, if one neuron in this 5 group is just, it just has a value of 1/5 of the other neuron, basically. So yeah, and of course, once you have these stronger neurons or these ones that are better for the loss, these will be used, and the other neurons might either become dead or be not used anymore. And this will be a waste of capacity. And yeah, once they start being not used anymore, they won't get any gradients, right? So that's extremely wasteful. And so dropout has been proposed to solve this issue. Dropout itself is based on 2 ideas. The first idea is bagging, which is a very general technique for reducing the generalization error by combining several models. You typically train different models on different data sets. So you can see it on the left side. This is the approach for bagging. Bagging actually stands for bootstrap and aggregating. So you have your original data set here, nicely depicted with these Easter eggs, and you make a couple of small training data sets. And on each training data set, which is now basically, if we're here, you make like you say like this is one training data set, this one, and this one in a way. And on each of these weird weirdly, or like subsets of training data sets, you now train one model. And then you aggregate the predictions of these. This is similar, or this is related to ensembling of models. And an ensemble, which is typically the way data science competition on Kaggle are won, is simply, as the name suggests, a combination of different kinds of models. These could be different neural networks. These could be neural networks that were trained multiple times, different architectures of neural networks. So one might be a convnet, one might be a transformer, another one might be a different convnet, for example, or even, constructed from different data sets. There's all kinds of ways to combine these predictions. You can simply average the output. So how you ensemble them is another parameter that we're not going to talk about because we're not talking about ensembling. We're just trying to explain why dropout will work or why it does work. So the idea of dropout is basically to make smaller networks within this network. So if this is your MLP, then we're going to try to find smaller networks that we're going to train to do the same task. And it basically, dropout is a strategy for making bagging practical for neural networks. You cannot really bag a large neural network that efficiently, because so bagging originally comes from very simple machine learning techniques where you can simply do this with 10,000, 20,000 times. So you split your data set into all of these. But for neural networks, this would become quite expensive. And so dropout approximates this. It approximates it in the following. During training, you simply set a bunch of neurons to 0. It's really simple. So you take your neural network and you simply cut some connections. How much you cut, you can set with a Bernoulli distribution. For example, you said, on average, we're going to cut 50%, and then you flip a coin that doesn't have a bias, basically. But you can also say, on average, you're going to cut 30%, which is basically a biased coin flip. And then afterwards, let's say you've cut 30% of the weights, and then you've got to reweigh the remaining activations that go to the next layer a bit. Because otherwise, since they are summed up, if you've cut 90% of them, only 10% of the signal will arrive, so you need to remultiply it so that the overall strength is still there. During testing, you then use all neurons. And this is a basic procedure. So simply by doing that, you reduce the co-adaptations and you reduce overfitting. One note here before we quickly go through how dropout works in practice is that dropout is not super common for larger scale data sets because it's much more difficult to overfit on large scale data sets. And later we'll also be talking about augmentations, which are heavily used for all kinds of data sets that also reduce overfitting. However, in a different manner, this is more common in nowadays called drop path and stochastic depth, which is basically, for the MLP case, you would be not only picking out random neurons which are set to 0, but you would actually remove a whole layer and let it go through the network as if that layer didn't exist. And that's called stochastic depth. And there's a bunch of methods or a bunch of training recipes which use that for training. Yes?
Are you picking different neurons that you're setting to activations to 0 for each epoch? Is that the idea?
No, so we'll go through the visualization here. So you actually, for each batch, for each step, you're doing this. So let's say this is your original model, and now you're going to pick these to be 0. And once you've picked these to be 0, your network is looking like this, right? So now you have a subnetwork, and you train it with this. Now you set these, for example, to 0. Now you have a very different subnetwork, and so on. And you effectively, and here I've just depicted all possible subnetworks for this graph. And obviously, some of these you cannot compute. So if you don't have inputs, for example, so ignore those. But basically, you're training a combinatorial many subnetworks. And all of these see different gradients. Well, they have a different architecture, basically. They see slightly different data because you vary the subnetwork per batch. And yeah, I'll go to the details in a bit more, but all right, then let's take a quick break. Yep.
The horse example.
Yes.
Horse
Yeah.
with the
Yeah.
noise. Maybe can I draw something?
Sure.
So, if there are a lot of, because I don't see the difference between noise and get stuck in a local minimum, I think, because if there are a lot of like pictures, just have this text.
Yeah. Yeah. Uh huh.
It's like, okay, we're fitting on noise, but I would say we're stuck in a local minimum. Or is there a difference?
Well,
Those, or?
yeah, because you don't see that. So in the let's say your training data set has like 70% of the horse pictures have a watermark and 30% do not. And let's say you want to test your thing in the real world, so none of them have a watermark. And now if you look at the training thing, it will simply look like this, right? It won't be seeing that there's a better way to learn horses than to simply identify watermarks. I mean, you could like, yeah, okay,
There will be a tiny one,
yeah,
because it's 30%.
yeah,
Or,
but or maybe actually if every image of the horse has like a horse's ear in it, it might even be better. That's true, but it's much easier to find this one.
Yeah,
and
okay.
so neural networks will cheat, and it's not just the optimization landscape, but yeah.
But it's much easier. But how can I see it in this loss landscape? How, is the loss much wider to get?
This is a tricky thing. So one thing generally is All right, let's continue. Let's look at the differences between dropout and bagging and dropout. So in bagging, all the models are independent, and each model is trained on its respective training data set. Now dropout has, as I said, dropout tries to approximate this, but is actually somewhat different. So the models share parameters. First of all, because they are simply subnetworks of a larger network. And you simply, because of the combinatorial complexity, you really cannot find all the models, and so you cannot really train all of them. And typically, each subnetwork encounters a different sub-data set, right? Because that's what I mentioned just before the break. Each time you mask out stuff, you are having a current batch that you're looking at. And if this current batch contains these sets of data, then this subnetwork is basically only trained using this set of data. Of course, the next time you arrive at this data set, you're picking a different batch because you always shuffle the batches, and you're picking a different subnetwork. And so you have this whole mixture going on. So dropout, that was a connection to bagging, but it doesn't contain this bagged ensemble of model, but also models that share these hidden units. So what this means is that each hidden unit must be able to perform well, no matter which other hidden units are in the model. So in a way, it's a kind of robustness. So if you have a model that was trained with dropout, you can easily kill some neurons, and it should be performing quite well. If you have a network that wasn't trained with dropout, if you pick out some random neurons, very likely the performance will degrade by a huge amount, because it simply wasn't trained for that. All right. And so what you can say is that dropout regularizes each hidden unit to not just be a good feature, but a good feature that's good in many contexts. And by context, we mean these subnetworks or even sub-data structures. All right, then let's move on to the fifth way to regularize data augmentation. A quote to start with is the best way to make a machine learning model generalize better is to train it on more data. I refer you also to the paper from Google, which was quite early on, called The Unreasonable Effectiveness of Data, and which basically tells a story that, okay, if you have a problem that's difficult to solve, don't spend too much time on trying to model it better or trying to optimize the loss function. Just get more data. This is like a paradigm which has existed in machine learning and computer vision for a while, and so far it's been very hard to disprove. As I said in the first lecture, I think we're getting closer, like in this decade or the next decade at least, to the place where simply scaling, simply using more data probably just physically isn't possible anymore. But so far data has been an important factor. However, real data is limited in practice, and by real data I mean specifically supervised data. And one way to create fake data is data augmentation. And let's look at the stars first. So the first star is labeled data in particular is limited. Unlabeled data you can get a lot. And data augmentation is not simply fake data, as we'll mostly see in lecture 13 on self-supervised learning, where data augmentations play a huge role. But the gist is that data augmentation can prevent neural networks from learning bad solutions because it can generate more variance in the training data set, which approximates the training data distribution, and thus can boost overall performance. Data augmentation techniques for computer vision include all these kinds of things. You flip the image, you rotate it slightly, you scale it, you crop it, you translate it, you add some noise, and you need to be sometimes a bit careful. For example, imagine the picture of a letter B. If you flip it, you end up with a D, depending on the type of font you use, and similar with 6 and 9. I should say not all of these augmentations are similarly often used across all contexts. For example, in object recognition and other kinds of data sets, you typically do not use rotation very much. You can think of like a couple of reasons why this is the case. Typically, actually rotation is unrealistic change, right? It's very rare that you get pictures in your test data set where you need to perform well that are shot upside down. So using that as an augmentation probably doesn't help that much, but that's flipping. Rotation is actually like 30 degrees or something in between. And once you start doing that, you start creating some artifacts, right? Like imagine if you do this, you get, for example, at the bottom, you get these black corners. You can cut them out, but even if you do that, simply this rotation operation on this 2D image will generate some artifacts which you probably do not want, which can, similar to this horse and watermark thing, decrease your performance actually. So you need to be very careful about these. For completeness, I added some augmentations which are commonly used in NLP. One of them is back translation. So you take your sentence, which is, I have no time, you put it through a Google Translate or whatever kind of translation software you have, you get the French version, and then you translate it back. So this way you simply generate some variants where the meaning is hopefully preserved. Another one is synonym replacement, just replace synonyms. So I have no duration. And again, this wouldn't be the perfect thing, but this could be done in an automatic way. That's the main important thing, that you can do it in an automated way. And then there's random insertion of words from the sentence, random deletion, random swapping of words, etc. There's all kinds of things. Basically, it makes memorization of the data set hard to nearly impossible. So you can think of especially crops, which crop is a word for like zooming into an image basically and taking that as a new image. Just like in Photoshop, you take crops, etc. For example, if you think about the amount of crops you can do for a 200 by 200 sized image, they're a lot. They're exponentially many. And so your network cannot simply learn the data set by heart in this way, especially once you start adding all kinds of color noises to this process. It makes memorization impossible. And all of these curves that I showed you earlier about the network being able to learn a data set by heart, that won't work if you start augmenting the images. So if you start applying augmentation, the network will not be able to learn shuffled labels anymore. One note about back translation is, for example, if you go from Hungarian to English, I think some of you might have seen this, and this is just a reminder that machine learning systems have bias all over the place, and we should always be careful about that sort of stuff. So in Hungarian, there's just one third-person word, which is, I don't know how to pronounce it, but you have this one, and then you translate it to English. And of course, it needs to pick one, because in English, there is no like a neutral form. And yeah, you can see that it just picks whatever was in the training data set the most common, very likely at least. And you end up with these very biased sentences, of course. And this is a fairly harmless example. But yeah, be very mindful about all kinds of things that, like, you think it's an augmentation. Well, actually, it's now generating bias, or might generate bias, depending on what you do. Some other computer vision augmentations visualized are here. These are actually ones which are like fairly commonly used, for example, on the right side, depending on the context again. And some of them really look quite nightmarish, and like that is surprising, but they help model training. And again, this is a point about, I mentioned this in the break as well, always look at the training data, and not only the training data, but also what kind of augmentations you're using. Like, for example, sometimes the augmentation might be doing something that you completely don't expect, and that's why your model isn't training. So that's important. There's also sometimes, depending on which package you use, your model, your augmentation expects a BGR image and not a red, blue, green, RGB image, red, green, blue. And if you confuse that, yeah, you will get very bad performances as well. not terrible performances, but just worse performances, and you won't be able to find the bug very easily. So data augmentation, as with all these other hyperparameters, is not a parameter. So you cannot run SGD on it because there's no loss signal coming from these augmentations. You can draw the computational graph, and you can see that there is no connection straight to the augmentations. What you can do is build a meta-learning loop around it. This could be like, for example, with reinforcement learning, where each game, in the analogy of Go, each game is a set of learning a model with these set of augmentations. And then the final performance will tell you how good was that, and then you can gradually adapt the policy that you use for augmenting images. Again, data augmentations is hard to tune and domain dependent, and we'll be going more about this in the self-supervised learning lecture, but one interpretation is augmentations are a way to incorporate what we know as humans to be trivial into a network. So otherwise, it wouldn't be very easy to say to the neural network, hey, actually treat all of these kinds of variations the same. And we're simply doing that by brute forcing it in a way. We're saying, okay, sometimes we use this augmentation, sometimes this, but the output should always be the same. For translation invariances and so on, you can actually build some things in the model itself. Yeah.
Has anyone trained a model to actually learn invariances, but then have humans label if these invariances are natural or not natural?
There are some papers from a Swiss group which basically analyze how models look at these augmented samples versus how humans look at them, and when humans get it wrong versus when machines get it wrong. Overall, the picture is that humans do quite different mistakes to models, but the mistakes that models are doing, so the way models are looking at these images basically, are getting closer to how humans are doing it, especially with the transformer architecture. Yes? I would say that's a good question for discussion. And the question was whether more data is worse for society, generally speaking, if your model is using more data. I would say it really depends, right? Like you can easily imagine a context such as medical, where if you have more data, your model will be better, you'll be able to save more people, in quotation marks, if it's that simple. While if you have less data, then your model won't be good or not useless, will not be useful at all. So I think there's, depending on the context, there's a good discussion potential for the amount of data. About privacy? Yeah, privacy is, I would agree, is directly correlated to the amount of data that's, yeah. So, or inversely correlated, yeah, sure. That's true. A model that has seen the whole internet probably has larger privacy risk than a model that has seen only synthetic data, for example. Yes, it's another important dimension. Yes?
Yeah, do you sometimes use data augmentation for the inference? So instead of just passing one image, you pass like 5, you get something more robust?
Yeah, that's a good question. So you do sometimes. Typically, in papers itself, you do the same evaluation that other people are doing. At some point, or depending on the domain, you actually do take, for example, multiple crops and average the predictions, and you get typically slightly better results. There's also a different kind of augmentation for inference, which is that you actually look at how does the model performance degrade when you start adding noise, or when you start, all kinds of noises, or when you start degrading the quality, for example, by compressing it with JPEG to a really bad shape. How does the model performance degrade? And that would be like a robustness check. So yeah, these are also used in that sense for inference. One important note is Yeah, in practice, you're right. Like in practice, it will probably cut off the person by a bit, etc. And you cannot ensure that this is nice. Yeah, but you pick this location to be random in practice. Yeah. All right. Cool. So we're back. We're back. Very good. Let's continue. There's just a slide telling you it actually works. Like augmentation is a major part of the current training pipelines. And you can see a bit in the plot on the right-hand side words like stochastic depth, dropout, repeated augmentations, gradient clipping, learning rate decay, weight decay, warm-up epochs, optimizer, batch size. Yay, you understand all of these words now. And there's a bunch more which you don't yet, but that's fine. Some of them, no, okay, I know all of them. Some of them we're not going to go into here. But anyways, so this stuff is being used. Let's quickly talk about other potential regularizations. You can simply add noise to the weights. Uncertainty, this sort of approximates uncertainty about the weights themselves. So if your weight estimator wasn't perfect, then what would you get? So you can approximate this by simply adding a bit of noise, and then the model needs to find solutions where it doesn't depend on the weight being exactly this number, but where the weight could be plus or minus a tiny amount, and it should still be giving a good performance. Label smoothing is kind of like this. So you're saying now the labels need to be not one hot, but a mixture of things. And typically what you do if you're not augmenting the input data themselves, what you do is instead is you're saying this is the real class, and everything else should be like just a tiny amount. For example, this should be predicted with like 0.9, and all the others should be predicted with 0.01 and so on. And what this does is it sort of makes the network be a bit more careful, and also it makes sense because not all the labels are really correct. So otherwise you're giving the network a bit of slack. And there's other properties why this actually works a bit better. But we're not going to go into the details here. You can use semi or self-supervised learning as well to regularize the model training, or you can have it learn or predict multiple things at the same time, right? So you can, instead of simply predicting the class of cipher image, you can have at some point of the layer also predict its reconstruct its image using some sort of autoencoder. Then you have two tasks. One is reconstruction and one is classification. And that can also regularize training. So it will have a harder time overfitting because now the task is much more difficult. There's a bunch of other ways to regularize as well. And I like this figure from the Understanding Deep Learning book in chapter 9. Which gives this nice sort of overlapping sets Venn diagram, essentially, of what these different things do. So make function smoother, increase data, in my opinion, with a quotation mark, because it isn't simply increasing the amount of data you have, but adding some prior assumptions there, combining multiple models, and finding wider minima, as I just mentioned. All right, so we'll move on to normalization. This is sort of the overview what we'll be talking about. First, normalization in the input space. Normalization, as I mentioned earlier as well, so we often have this ill conditioning going on, and normalization is a way to reduce this in the weight space. In the input space, this is especially useful because it allows us to treat all the features that are now on a similar scale. So imagine if you have an input that looks as follows. You have the original data, so it clearly has a higher variance in the y dimension or in the x2 dimension than it has on the horizontal dimension. So what you can now do is you can subtract the mean, and then you can divide it by the standard deviation. And now you have data simply linearly transformed, right? Subtracting mean and dividing by a number is a linear transformation. But now the data sits in this, or roughly in this 0, 1 square. So the input variables roughly follow a Gaussian distribution. And now you have all the nice properties that come also with the initialization of the neural network weights, that now if the input data is roughly Gaussian, then we've initialized the model to deal with models that are, deal with inputs that are roughly Gaussian, to keep the variances throughout the network. And this procedure is extremely standard, such that, you need to, for ImageNet, for example, these are these values, and by the time you finish a PhD, you often know these values by heart, which not sure to be proud or sad about, but this is important. Like sometimes there's a difference between, for example, in TensorFlow versus in PyTorch. Sometimes, because these values are just approximate, like they don't need to be exactly like that when you train. So when you train, you could easily be using 0.5 for all of these, because they're roughly 0.5. They're not exactly the mean and standard deviations, but they're good enough for training. But then your neural network expects images to be normalized this way. So this is very important. You need to, if you take a model that was pre-trained, you need to remember you need to find how the input data was normalized. Importantly, this is a linear transformation. The first layers or anything that happens in a neural network at first is a linear transformation as well. And two linear transformations, you can merge them back together. So in the end, you don't need to normalize this anymore if you wanted to. You could simply merge this subtraction of mean and division by a sigma into the first layer if you wanted to. And you would save a bit of computation when you deploy it to the real world, for example. All right. The main point is, however, the normalization of intermediate layers. We'll be talking about these bunch, and you can see that layer normalization has recently become a lot more popular and is actually, for the most part, the way to go. But batch norm has traditionally been extremely important, and there's reasons for all of these other normalizations to be around as well. All right, so batch norm. Here, the basic idea is that we use activations from the previous layer as inputs to the new one. And the high-level goal is to make neural networks train faster. And importantly, to train in a stable manner. So this was a major innovation that batch norm did. It showed that you can train neural networks faster and easier. As the name suggests, it deals with batches. So you need to have batches here. And this plot, for now, you can see that the horizontal dimension here is the mini-batch samples. So that's the dimension that we'll be looking at for batch norm. And it will be much clearer when you compare the different normalizations with each other. It's typically applied before activation, yeah. Let's see what it actually does. So what it does is normalizes the inputs to this batch norm layer. So it's a particular layer. It normalizes them in a way such that the input is roughly 0, 1 distributed, but then it learns another linear transformation of that. So after you have normalized it, so AL, you then multiply this AL with a fixed value, and you add a bias term again. So these are trainable. These can get gradients and do get gradients. And these are for rescaling and shifting. So basically, you put everything back to 0, 1, and then you can learn how much to shift it or scale it for the next layer to work really well. So the computation looks as follows. So you simply, this mu j and sigma j, you simply compute from the mini batch. So let's say you have m examples in your mini batch. These would be the formulas that you use to compute. And once you've done that, you normalize your data. That's the normalized row. And then you multiply it by gamma and add this beta. There's a, yeah?
What's the epsilon in the normalization?
Right. Good point. Good point. So epsilon is, you might have seen that in, I think, in the Adam optimizer slide as well. Epsilon is quite often added to all kinds of division operations simply such that they don't explode if you do encounter a 0. Yeah. And you can do the math yourself. As long as epsilon is small, it basically doesn't have any effect at all on this computation. But at least it won't give you like a infinite value when you do things numerically. There's a hypothesis why batch norm helps, but this hypothesis is like very dubious at best. So we're going to skip this one. This is not just my opinion, but this is you can find the same in textbooks as well. What it does, however, is it makes the loss landscape a lot smoother, and it helps with training. So here you can see basically the loss landscape when you use batch norm versus when you don't use it. There's some theoretical results which show that the Lipschitz nets, how Lipschitz the layers are, is improved by that. So basically each layer doesn't significantly change the outputs by that much, which helps the gradients flow a lot better through the neural network. Yeah, and you can basically, when it came out, it basically allowed training by orders of magnitude faster while keeping the same performance. Recently, and that's very recently, people figured out how to do the same without using batch norm, but it requires quite careful initialization. Benefits I have mentioned: you can train faster, or in turn, it allows you to use higher learning rates. It reduces overfitting. Overall, it really was fundamental to making neural networks, deep neural networks, train well. And yeah, gave better results. At this point, a quick quiz. How would you use batch norm at test time? So I've described how you use it during training. But now what do you do at inference? Do you, number one, go through the data set in a predefined order? 2, go through the data set, the validation set, in a random order, predefined, random, or you go through the data set in random order multiple times and then averages, or you simply skip the batch normalization layer. So have a quick think about it. And then 1, 2, 3. 3, 3, 4, 3, 4, 2, 4, 3, 4, 4, 3, 1. All right. So I will allow 4, but all of these are actually wrong. Because, I mean, so what the batch norm layer is doing, well, actually, let me just go back to the slide. You saw what the batch norm layer is doing, right? It's normalizing the data, and it's doing some sort of linear transformation. If you simply skip it, well, your features are not going to match what the next layer is expecting, so it's not going to work. I said I'll allow it because potentially what you meant is what will actually happen. So it isn't quite skipping. But what you do is you skip the computation part. You simply use what you had during training. So you simply keep a memory of, and this is now the solution, you keep a memory of the mean and the standard deviation, which you need to save somewhere per layer and per feature dimension. And you keep that and you use that during inference. Yes?
In the last lecture, when we went through timing initialization, we said that it was used to preserve the variance of the weights through the neural network. Is this type of initialization necessary if we use batch normalization? Is the variance kind of going to be always maintained with the normalization?
It still helps. I think it makes batch norm might make learning even weirdly initialized neural networks better, but it will still help a lot. Yeah.
Why do we have to learn gamma and beta? Because the next layer will be a linear layer, and a linear layer followed by a linear layer is another linear layer. So we could just assume they would learn those per
Yeah, yeah, that's a good point. In practice, you don't have to necessarily. It works a bit better, though. It does this normalization and scaling, so that is favorable for just learning the next convolutional layer. What you, quite often do is you skip the beta part, because for example, if you have a layer before that, it's already doing some sort of linear operation, x plus beta, so now you don't need to have another beta parameter. Regarding the skip, how do we ship? Oh no, yeah, you cannot simply go through the batches in a predefined order. This would be the worst solution, because in a predefined order, your data samples would be ordered by class, and batch norm normalizes the data, right? So you end up at between -1 and 1. And often what follows a batch norm is a ReLU. So it would make everything 0. But if the samples come from the same class, it's the worst kind of thing, because they're all similarly distributed. So you might be really making random things to 0. And you can test this yourselves. If you have random batches, then the stuff that gets zeroed out by batch norm plus ReLU is sort of the same as training, but it won't be reproducible. And yeah, you could go through the test data set multiple times, but what we usually do is we keep a moving average of these numbers. There's a bunch of disadvantages. Well, it doesn't work with a mini batch of size 1. The performance is sensitive to the batch size. You need to store all these batch statistics that I just mentioned, the running mean, the running sigma. You have this difference of how evaluation is done between training and testing, which means whatever you use for training will be used for inference as well. Yeah, there's a bunch of problems. And it's very often the reason for bugs. There are more reasons, actually. And one reason that I'm just going to briefly mention is multi-GPU training, which is very common, where typically what you have is you take your neural network and you copy it to every GPU. Well, the package does it automatically. And then you have your batch, and you simply send this random set of data to this GPU, this set of data to that GPU, that set of data to that GPU. But now, obviously, you're computing the mean and sigma, and they will be different for every GPU. And now, if you're trying to compute the gradients, you will get gradients which were computed in a different manner, because every single layer on every single GPU will have had slightly different statistics. So what you'll need to do in such a case is you need to have communication between the GPUs at every step, at every time you have a batch norm going on. Otherwise, you will be using slightly noisy estimates, which especially for small batch sizes won't be very good. All right, moving on to layer norm. Here's quickly the overview what layer norm does. It's fairly simple. So in the batch norm, the batch is now in the x dimensions, so you have 3 vectors. And batch norm simply goes through the batch in such a way that for each feature dimension, you have the mean and the standard deviation. And you subtract this and you divide it by, and so on. And layer norm now simply goes the other way. It doesn't have any dependency on the batch now. It simply, per sample, computes the mean and the standard deviation and does this for all the feature dimensions. So it was originally introduced for recurrent neural networks, but the benefits are that it performs the same during training and testing, and this is how it's computed. So now you compute the mean over features, so not over samples, but over features. Same for the variance, you normalize it, and again use scale and shift, which are, again, parameters. And this one works extremely well. So if you zoom into one of these the images where the best performances are achieved with augmentation and so on, I think somewhere there must have been, or maybe it wasn't mentioned there, is layer norm. So layer norm is replacing batch norm for a bunch of computations nowadays. Finally, you can keep going at this game, basically, and now you have instance norm. It's similar to layer norm, but now it's per channel and per training example. So we had this box, right? And now we're simply going to cut this further in the channel dimension, and you end up at this slicing of the cube. So the idea comes from which part was it? I think from stylization of images, from style transfer. And the idea is basically the network should be agnostic to the contrast of the image. So that's why you compute it across the feature's spatial dimensions. And it's literally the same computation as batch norm, except that you do not do the summation across the samples. It's not used for other tasks than style transfer. Finally, we're going to talk about group normalization. So now you can see that we're sort of splitting this cube into two different things. And so it's now the same as instance norm, but over a group of channel. So here's a comparison. So if we have the number of groups be equal to the number of channels, then we're at instance norm. So basically, yeah, you can split each of these two boxes one more time, and then you can see, okay, what we're computing is instance norm. If we have just one group, then we're back to layer norm. And this is a really flexible interpolation basically between these two. It often works quite well. And it's very important as in their use for group convolutions. So group convolutions follow the same idea by basically saying this half of the neurons is only connected to the next layer's other half of the neurons. And so you're basically restricting the connectivity matrix of the different outputs. So in the RGB case, this would be saying something like, okay, the first 5 convolutions only look at the red and green channel, and the next 5 convolutions only look at the blue channel, for example. This would be, you wouldn't do this in the first layer, but you can think of how it generalizes for subsequent deeper layers which have, for example, 500 dimensions. And then you can easily split this between a set of 200 and another set of 250 and things like that. So this is a somewhat older plot of the typical learning curves for ResNet. Nowadays, you can get the learning curves or the performance even better with layer norm. All right, then weight norm. The weight norm is a simple way to help training. So what you do is you take your weights. In this case, the weights would be initialized with a V. You simply normalize the weights. So you have weights which are just a direction. And then you learn the magnitude of this direction, G. So now you have another parameter, G. And all the weights are learned in this split manner. So you learn the direction and you learn the magnitude of the weights, basically. And it can be combined with all kinds of other normalizations and typically works well. Yeah. So here's the references for these papers. There's just a few more slides, so I think we'll be done in time. About hyperparameter tuning. So hyperparameters are, as I've mentioned already, the stuff that you cannot train with stochastic gradient descent. What you can do is the following, which is called graduate student descent. So that means simply you run a bunch of examples and you run a bunch of experiments and then you find the best one. So, and this is the visual depiction of what grad student descent might look like. So it seems to be quite tricky. So also this model seems to know how grad student descent feels like. So that's pretty good. But yeah, more seriously, the learning rate, I've mentioned how to tune it the last time. So just these learning rate schedules. So that you can literally take from the last time slides. Again, cosine decay is probably good, plus warm-up if learning rate is now very common. Typically, you try these things for the starting learning rate. You try these things at different orders of magnitude, and you look at the validation error. And same with the learning rate decrease. A quiz at this point is the following. So you have this red training curve, which follows the blue curve for the initial few steps and then jumps up to the top, and then after that starts decreasing again, but ends up always higher than the blue curve. So let's say you ran your model once and you end up with this red curve, and you ran it another time and you had the blue curve, which is quite weird. So you're clearly seeing a difference. So what do? Do you, number one, check the individual values of the gradients, check the batch at which the loss exploded. 3, try increasing the batch size or lowering the learning rate. Or 4, all of the above. So what do you think? 3, 2, 1. So 2, 3, 4, 2, 2, 3, 4. Someone's hedging their bets with 2s. Yeah, pretty much all of the above, I would say. I mean, obviously, if you find the bug with one of these, you can stop. But all of these would be valuable approaches. So it could easily be that the red one picked a sample which completely put the model in the wrong direction. But that only happened probably because the learning rate was too big. The learning rate was probably too big in relation to the batch size, and so on and so forth. So all of these would be valuable ways to debug this. And these logging tools are extremely important for seeing that, for example. If you were just looking at the learning rate, you would be quite wondering why after 2 days your performance is like slightly worse than it was with your other run, but you wouldn't have seen this spike, for example. Dropout rate, you would typically start with small values. And you would try this with larger networks. As I said, with batch size, typically start with a small one, but generally as much as can fit the GPU. Design choice of the architecture itself, don't try this at home. Pretty much take models that exist. And the same goes for all the other hyperparameters like learning rate. These are quite really informative papers to read, where you can figure out, okay, all of these architectural choices that also we're going to go through in the next 2 lectures actually for ConvNets, how they can be further optimized. But if you had to design your own neural network, generally start from small sizes with a few neurons and then increase complexity and reuse the existing hyperparameters. I'll start off with some important notes about how to babysit or how to what to do when training these neural networks. The most important one is when you train these, establish a baseline. First of all, what does a random neural network do? What does a linear regression give you? What kind of performance? What is random chance in the case you're doing classification? In the case of random chance, you would be expecting, for example, for Cypher to get 10% accuracy because there's 10 classes. Then what kind of loss does this translate to? Well, the loss would be the cross-entropy loss. So it would be the negative log of 1/8, and that would be the expected loss function that you would expect, for example, at the beginning of training. That's what I just said.